All right, this is lesson 10 from module 5. We're going to be talking about increasing and decreasing functions. So Archimedes is one of the most well-known mathematicians in all of history. When asked by the king of Syracuse to determine if a crown was pure gold, Archimedes took the challenge. He discovered his answer while taking a bath, and he realized that when he got into the tub, a certain amount of water was displaced. He could do the same with the crown. Excited, he screamed, "Eureka!" and took off to tell the king. So we are going to control the level of water in the bathtub by turning on and off the tap, taking the plug in or out, and having Archimedes get in and out of the tub. This will create a graph relating time and depth. So we're going to label the bottom axis as time. So that's going to be how much time is passing. And we're going to label this one as depth. This is the depth of the water. Now, what we're going to do is we're going to create a little story, and we're going to graph our story based on what we're talking about. So let's create the story. So step 1, we're going to turn the water on. We're going to fill the tub up. Okay. Now, when you do that, we're always starting at 0 water in the tub. When you start filling the tub at a constant speed, it's going to look like this. It's going to increase, positive slope. This is step 1. And it's going to start filling the tub. Now, step 2, we're going to put the plug in. Now, when you put the plug in, it's going to start filling faster because the water's not draining out. So we're going to have a steeper slope, still increasing, but at a steeper rate. Okay, step 3, we are going to turn the water off. Now, if you turn the water off, that means that the level of water is going to stay constant. It's going to go straight across. Step 4, let's have Archimedes get in the tub. So Archimedes gets in the tub. Now, what happens is the water, as soon as he gets in, is going to go straight up because he's displacing the water. So that would be step 4. Step 5, Archimedes is going to stay in the tub. Okay. When he stays in the tub, nothing is happening. The water level is not changing. So that would be a constant line just directly across. Step 6, we're going to have Archimedes get out of the tub. So Archimedes gets out. Now what happens is the water is going to immediately drop down to the same level it did when he got in. Step 7, we're going to have the water sitting in the tub, nothing happening. So that means that it's going to go straight across. There's no movement. That's step 7. And step 8, we're going to take the plug out. And drain. So what's going to happen? It's just going to start decreasing until it is empty. So that would be step 8. All right, so part A, what would be the fastest way to overflow the tub? Okay, well, the fastest way is if he got in the tub, he plugged the tub, and he put the faucet on full power, right? So that would be that Archimedes gets in the tub. He plugs the tub. And you put the faucet on full blast. Part B, describe the conditions under which there should be no change in the level of the water. Well, if the plug is in and the water is off, then it should not be filling, it should not be draining. It should be just staying constant. All right, so let's look at another example. Okay, this time it says the graph below represents the total number of smartphones that are shipped to a retail store over the course of 50 days. So here's our graph. We're going to go based on time and the number of smartphones. It says read through the scenarios and sketch the graph of the function that models the situation. So the first part says the production scheduled was normal and smartphones were shipped to the retail store at a constant rate. So we're shipping out smartphones, sorry. Okay, constant rate means it's going up at the same speed. So actually, I'm not going to call it A, I'm going to call it I, or 1. Okay, so that is step 1. Step 2 says a defective electronic chip was found and the factory had to shut down. Well, if it's going to shut down, no smartphones are going to be shipped. So that's just going to stay at a constant speed. So that would be step 2. And then half of the factory workers went on strike and not enough smartphones were produced for normal shipment. So it's still going to be increasing, just not at as fast of a rate as the first one. So this would be step 3. Now, when you're shipping out smartphones, that would be considered a positive slope because the number is increasing. If there is no smartphones being shipped, that would be a 0 slope. Okay, it would be a constant value of smartphones. And then this one, like we said before, it's still going to be an increasing or positive slope, just less steep than part 1. All right, step 3, or number 3. The graph below shows the distance from Lewis's home as he walks his dog in the neighborhood. Describe the change in the distance from his home over the time. So this is time compared to distance. So we're going to write a little story that might be happening according to this graph. So this first part right here, he is getting further and further from his home at a constant rate. So we could say that Lewis is walking away from his home. Now, 2, he is actually staying the same distance from his house for a little bit. So maybe he stops on his walk, maybe gives the dog a treat. Okay, so he stops. Maybe he stops for ice cream. He's walking his dog, so he stops to give his dog a treat would be. That would be appropriate if you're walking your dog. And number 3, we start increasing again, getting further from his home. So he continues to walk away from his house. And then the last one, he turns around. He must be coming back to his house as he gets closer and closer. So he turns and heads back to his house. All right, so let's go to the next page. Now that we've talked about graphing stories as we are increasing or decreasing at a constant rate, let's continue this with some real-world situations that can be modeled by linear functions. So there are times when nonlinear functions are needed to describe the relationship between any two types of quantities. Let's compare these two scenarios. So alpha is running at a constant rate, so constant rate meaning it's going to be linear, on a flat paved road. The graph below represents the total distance he covers with respect to time. So in your own words, let's describe what's happening as he's running during the following intervals. So from 0 to 15, so that's this right here. From 0 to 15, okay, he is running. Oops. He runs. Now he's actually running 2 miles. And that's a course of 15 minutes. So he runs 2 miles, 15 minutes. From 15 to 30, Okay, so now he's going from 2 to 4, so he runs another 2 miles. Still in 15 minutes. Now I'm just going to make a note here. That's a total. He's gone 4 miles so far. Total of 4 miles. All right, so now I want to go from 30 to 45. He's going to run another 2 miles, total of 6 miles. And that's a total of 6 miles. And the last one, he is from 45 to 60, goes up to 8 miles total, so that's another 2 miles. Still 15 minutes. And that's a total of 8 miles. So notice that this is all increasing at a constant rate. That's what makes it linear. All right, now let's compare that to the next column. Okay, now we don't have a linear situation. Shannon's running on a rocky trail that's initially flat and then leads to a steeper mountain. So the graph below represents her distance covered. So let's describe in your own words what's happening as Shannon is running during the following interval. So from 0 to 15 minutes. So that looks like she's covering about 1.5 miles. So Shannon runs about 1.5 miles in the 15 minutes. All right, let's look from 15 to 30. So it looks like she's running about just over 0.5 mile, so maybe 0.6. So Shannon runs another 0.6 miles in the 15 minutes. So that's a total of 2.1 miles. All right, let's look from 30 to 45 minutes. Looks like she's running about another 0.5 mile. So Shannon runs another 0.5 mile in the 15 minutes, and that makes your total of 2.6 miles. And then from 0.45 to 0.6, it looks like she's only running about 0.4 miles. So Shannon runs another 0.4 miles in the 15 minutes, which totals 3 miles. Now notice that her distance is still increasing. It's just not increasing at a constant rate. So it's still increasing, but not at a constant rate, which makes it nonlinear. All right, so let's look at the next page. Now, we just talked about how the rate of change for a function can provide useful information about a relationship. A linear function has a constant rate. A nonlinear function has a variable rate, meaning a changing rate. So let's just look at these pictures. So this would be increasing at a constant rate, meaning it's linear. This would be increasing just not at a constant rate, which is why it's nonlinear. This would be decreasing at a constant rate, linear. Decreasing but at not a constant rate, which is nonlinear. Now, if you're looking at a table, okay, linear functions will have a consistent rate of change. So this is increasing by 3, increases by 1, increases by 3, increases by 1, by 3, by 1, by 3, by 1. So you notice that your slope is 3 over 1 for the whole table. Now this one, this increases by 2, increases by 1, increases by 2, increases by 1. This increases by 4, but still only increases by 1. Increases by 8, still only increases by 1. So you have a slope of 2 over 1 in the beginning, which becomes 4 over 1, which becomes 8 over 1. So notice that all of the rate of changes are different, which is what makes it nonlinear. All right, so let's do some practice problems. Let's turn to the next page. I'm going to have you do this on your own, so hit pause, complete the next 2 pages. When you're done, you can hit play. Just make sure that you have the correct answers. So, Nika took her laptop to school and drained the battery while typing a research paper. When she returned home, she connected her laptop to power source and battery started recharging. So let's sketch a graph here. So we're going to do the battery charge with respect to time. So when she gets home, she's going to start charging the battery. So it goes from 0 at a constant rate. It's just going to start increasing at a constant rate. So that's going to be a linear function. So is it linear or nonlinear? It's linear. Okay, and you can just say the battery is recharging at a constant rate. Part B is the function represented by the graph increasing or decreasing. Now this is going up, so we call that increasing. And that's because the battery is being recharged. All right, next page, number 2. Lamar and her sisters are riding a Ferris wheel at a state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution, meaning it goes around 1 time. The graph below represents Lamar and her sister's distance above the ground with respect to time. Is the function represented by the graph linear or nonlinear? Now, if you look, this is nonlinear, not a line. So where is the function increasing? And what does this mean within the context of this problem? So let's go through and see, where is it increasing? So it's going to be increasing from 0 to about 4 seconds. So 0 to 4 seconds. Now it starts going down, but then from about 8 to 12 seconds, it starts going back up, comes down again. So it goes up 16 to 20 seconds. Remember, it takes 8 seconds for a full revolution, so I'm just skipping every 4. Okay, so it goes down again from 16 to, or up, down again. Then from 24 to 28, it's going up, comes back down. From 32 to 36, it's going back up. Now, we know that what that means in the context of this problem is that they're going up on the Ferris wheel. They're going into the air. So Lamar and her sisters are rising into the air. All right, part C. Where's the function decreasing? Well, if it's increasing at all these place values or time slots, we're going to be decreasing during the rest of the time. So we're going to be decreasing between 4 and 8 seconds. So coming down, goes back up, comes down between 12 and 16 seconds, 20 and 24 seconds, 28 and 32 seconds, and then 36 to 40 seconds. So what does that mean in the context of the problem? That's when they're coming down on the Ferris wheel. So Lamar and her sisters are traveling back towards the ground. All right, part D. How high above the ground is the platform for passengers to get on the Ferris wheel? So look at the lowest the Ferris wheel goes is about 5 feet. So that would be where the platform is. That's where you would get on. So the lowest point is 5 feet, which is what the represents, or what would represent the platform. Part E, based on the graph, how many revolutions does the Ferris wheel complete? So let's look. It would be going up and down, that's 1. Up, down, that's 2. There's 3, there's 4, and there's 5. So according to this graph, we're looking at about 5 revolutions. Now, what is the diameter of the Ferris wheel? So looking at this, the platform we said was at 5 feet, and the highest point it's going is at 45 feet. So if it's going from 5 to 45 feet, we're talking about the wheel. I can draw it for you. Here's the 5 feet. Here's 45 feet. The diameter goes all the way across, which would make the diameter 40 feet. Because the lowest point is 5, the highest point is 45. All right, I'd like you to try the problem set for these, showing when things are increasing and decreasing. Be creative in the problem set. Sometimes they're going to ask you to come up with the story. So let's see your creativity come through in those problem sets.